February 3rd, 1945. The dark sky above Berlin, Germany. Technical Sergeant James Donovan hunched over his instrument panel in the cramped upper turret of the lead B-17G flying fortress. The temperature outside registered -38 degrees, yet sweat beaded on his forehead. His oxygen mask fogged with each labored breath as he monitored the engine gauges with growing concern. The squadron of 23 B-17s from the 301st Bombardment Group had maintained tight formation through heavy flak, their Wright R-1820 Cyclone engines straining at maximum power settings as they climbed to 27,000 feet. The Berlin raid marked their third consecutive maximum effort mission. 3 days, 3 cities, 3 chances to die. "Number 3, running hot again, Captain," Donovan reported through the intercom, his eyes fixed on the temperature gauge climbing past the red line, oil pressure dropping. Captain William Hayes, the pilot, didn't respond immediately. The violent shuddering of the airframe as flak burst around them made communication difficult. The formation ahead was already down 2 fortresses, their burning wreckage spiraling toward the German capital below. "Or how bad?" Hayes finally asked, his voice tense but controlled. 260 and climbing, Donovan answered, referencing the cylinder head temperature in degrees Celsius. "Overheating just like yesterday. She'll seize if we push her much longer." Hayes banked slightly, adjusting their position in the formation. A Messerschmitt Bf-109 streaked past their starboard wing, pursued by a P-51 Mustang escort. The brief aerial ballet seemed almost peaceful compared to the mechanical time bomb ticking within their own aircraft. "Can you nurse her through the bomb run?" Hayes asked. Donovan stared at the gauge, watching the needle continue its relentless climb. "Maybe," he answered, "but I'm cutting power to 70%. We'll fall behind if I go lower." "Do what you can," Hayes ordered. "We drop in 4 minutes, then we turn for home." Home. The word seemed impossibly distant. 300 miles of enemy territory stood between them and the English Channel, and their B-17, nicknamed Angel of Vengeance, was flying wounded. The constant cycle of overheating engines had become their most reliable enemy, claiming more bombers than German fighters in recent months. As the bombardier called out range to target, Donovan focused on the gauges, willing the temperature to stabilize. The modified cowl flaps he'd installed last week had helped on previous missions. But the extreme cold of high altitude combined with the engine's maximum power demands created a deadly engineering contradiction. Components that needed cooling were overheating, while others were freezing. The fortress shuddered as the first bombs dropped from its bay. Donovan knew they'd committed now, lighter, but still struggling with an overheating engine that threatened to transform their aircraft into a 20-ton coffin falling from the sky. 260 and climbing, Donovan answered, referencing the cylinder head temperature in degrees Celsius. "Overheating just like yesterday. She'll seize if we push her much longer." Hayes banked slightly, adjusting their position in the formation. A Messerschmitt Bf-109 streaked past their starboard wing, pursued by a P-51 Mustang escort. The brief aerial ballet seemed almost peaceful compared to the mechanical time bomb ticking within their own aircraft. "Can you nurse her through the bomb run?" Hayes asked. Donovan stared at the gauge, watching the needle continue its relentless climb. "Maybe," he answered, "but I'm cutting power to 70%. We'll fall behind if I go lower." "Do what you can," Hayes ordered. "We drop in 4 minutes, then we turn for home." Home. The word seemed impossibly distant. 300 miles of enemy territory stood between them and the English Channel, and their B-17, nicknamed Angel of Vengeance, was flying wounded. The constant cycle of overheating engines had become their most reliable enemy, claiming more bombers than German fighters in recent months. As the bombardier called out range to target, Donovan focused on the gauges, willing the temperature to stabilize. The modified cowl flaps he'd installed last week had helped on previous missions, but the extreme cold of high altitude combined with the engine's maximum power demands created a deadly engineering contradiction. Components that needed cooling were overheating, while others were freezing. The fortress shuddered as the first bombs dropped from its bay. Donovan knew they'd committed now, lighter, but still struggling with an overheating engine that threatened to transform their aircraft into a 20-ton coffin falling from the sky. Chapter 2. Context and Fatal Flaw. 8 months earlier, Ridgewell Airfield, Essex, England. May 1944. Technical Sergeant James Donovan stood in the pouring rain, watching the ground crews roll the charred remains of a B-17F into the maintenance hangar. Another engine fire, another crew lost. The 7th that month for the 381st Bombardment Group. Same problem? Asked Major Robert Franklin, the group engineering officer, lighting a cigarette despite the rain. Yes, sir, Donovan replied. Number 3 engine again. Looks like cylinder head overheating led to catastrophic oil line failure. The Wright R-1820 Cyclone radial engines that powered every B-17 were mechanical marvels, delivering 200 horsepower each at takeoff. But they harbored a critical flaw that became increasingly apparent with each bombing mission: inadequate cooling of the rear cylinder banks, particularly under sustained high-power operations at extreme altitudes. Major Franklin walked slowly around the aircraft, examining the scorched metal where flames had engulfed the starboard inner engine nacelle and wing. Thermal engineers at Wright Field said this wouldn't happen above 20,000 feet. Too cold up there, they said. Donovan nodded grimly. Theory versus reality, sir. We're seeing cylinder head temperatures spike to 280 degrees Celsius during maximum power climbs. The spec says they shouldn't exceed 232 degrees. The Wright R-1820-97 engines on the G-model Fortresses represented years of incremental improvements to the original design, yet the fundamental cooling problem persisted. The rear cylinders, particularly numbers 5, 6, and 7 on the 9-cylinder radial, ran significantly hotter than the others. The standard baffles designed to direct cooling airflow became less effective at high altitudes where the air was thinner. The situation worsened during the long missions to Berlin. 4 hours of sustained high-power settings, repeated exposures to flak requiring emergency maneuvers, and the heavy defensive armament of 13 50-caliber machine guns all contributed to excessive heat buildup. When the rear cylinders overheated, piston rings failed, exhaust valves warped, and oil lines ruptured, turning the meticulously engineered power plant into an incendiary bomb attached to the wing. Inside the hangar, Donovan walked to the maintenance records board. Red marks dominated the chart, each representing an engine change or failure. B-17G formations departing at full strength rarely returned intact, with at least 1 or 2 aircraft falling out due to engine problems before ever engaging the enemy. The 8th Air Force lost 47 Fortresses to engine fires last month alone, Major Franklin said, reviewing a classified report. That's more than the Luftwaffe shot down during the same period. Donovan ran his hand along the engine cowling of a B-17 undergoing maintenance. The standard design featured a series of adjustable flaps around the circumference that could be opened or closed to regulate airflow. But the system had been designed for operations in the Mediterranean and Pacific theaters, not the frigid conditions of high-altitude operations over northern Europe. What if we're approaching this all wrong, sir? Donovan asked suddenly. Everyone's focused on getting more cooling air to the engines. But what if the problem isn't insufficient airflow, but improper distribution? Franklin looked up with interest. Go on. The air baffles direct cooling flow primarily to the front cylinder bank. At high altitude and maximum power, the rear cylinders are getting starved of cooling. It's why we always see failures on cylinders 5, 6, and 7. And your proposed solution? Donovan hesitated, knowing his idea violated Boeing's engineering specifications. I want to modify the internal baffling to redirect more air to the rear cylinders, even at the expense of the front bank. The front cylinders have margin to spare. Sounds reasonable, Franklin said. Well, so what's the catch? To do it properly, we'd need to modify the engine cowling itself, and that requires cutting into the nacelle structure, something the technical order explicitly prohibits. The Major took a long drag on his cigarette, his expression unreadable. So you're proposing unauthorized structural modifications to combat aircraft? Yes, sir, Donovan answered without hesitation. The alternative is losing more bombers and crews. Franklin crushed his cigarette under his boot. Draw up the design. We'll test it on one aircraft. But if this goes wrong, Donovan nodded, understanding the unspoken warning, I'll take full responsibility. June 1944, Maintenance Hangar 3, Ridgewell Airfield. Donovan worked through the night by the dim yellow light of an inspection lamp, his hands covered in graphite and metal shavings. The unauthorized modification to the B-17G before him had to be completed before the morning inspection. If discovered prematurely, his experiment would be shut down and his career likely over. The solution he'd developed was deceptively simple, but required precision machining of critical components. Using scrap aluminum from damaged aircraft, he had fabricated a series of curved deflectors that would redirect the cooling airflow inside the engine cowling. The design resembled a reverse scoop, a shape his colleagues had mockingly called ridiculous when they first saw his sketches. "It'll never work," Technical Sergeant Willis had said. "You're pushing air against its natural flow path. Basic aerodynamics says you'll just create turbulence and make the problem worse." But Donovan's calculations, worked out on the back of maintenance logs and flight manuals over countless nights, suggested otherwise. High-altitude air behaved differently, and the extreme temperature differentials between the cylinders created opportunities for ingenious solutions. The most challenging aspect was modifying the cowl ring itself. Boeing's design was an integrated part of the nacelle structure, not intended for field modification. Using a small cutting torch and file, Donovan carefully shaped a series of new vent openings positioned directly behind cylinders 5, 6, and 7, the problematic rear bank that consistently failed. Each vent featured a small aluminum deflector angled to capture and direct the slipstream into the engine compartment at precisely the right angle. The modification looked crude compared to the aircraft's factory-finished components, but Donovan knew aerodynamics cared about function, not appearance. "You're really going through with this?" asked Sergeant Merrill, the night shift supervisor who had agreed to look the other way. "Have to," Donovan replied, not looking up from his work. "We lost another one yesterday. Engine fire over Hamburg. Entire crew." Merrill handed him a socket wrench. "Well, what about the winterization kit Boeing sent last month? Isn't that supposed to fix the overheating?" Donovan snorted. "The winterization kit solves the wrong problem. It helps the engines start in cold weather, but does nothing for high-altitude cooling under load." The irony wasn't lost on either man. The B-17's engines simultaneously suffered from being too cold on the ground and too hot in the air. Boeing's engineers, working from their desks in Seattle, couldn't reconcile the contradictory requirements of European theater operations. As dawn approached, Donovan made the final adjustments to his modification. The system now included a series of small deflector plates inside the cowling that would direct more cooling air to the rear cylinders while slightly restricting flow to the overcooled front bank. The external vents would provide auxiliary cooling specifically targeted at the hottest areas without disrupting the overall aerodynamics of the nacelle. The real innovation, however, was how the system would interact with the existing adjustable cowl flaps. By strategically positioning his additional vents, Donovan created a pressure differential that would actually increase cooling efficiency as airspeed increased. The opposite of conventional designs that lost effectiveness at high speed. "This breaks at least 17 different technical directives," Merrill observed, examining the completed work. 18, Donovan corrected him, wiping grease from his hands. "I counted." The maintenance chief arrived at 600 hours, followed by Major Franklin. Both men inspected the modified engine nacelle with professional skepticism. "You're creating turbulence inside the cowling," the chief said immediately. "That's going to cost us performance." "Only at low altitude," Donovan countered. "At operating altitude and cruise speed, the pressure differential actually streamlines the airflow around the rear cylinders." Major Franklin walked slowly around the engine, studying the modification from different angles. "Which aircraft is this going on?" "Angel of Vengeance," Donovan answered. Captain Hayes volunteered. "They've had 3 engine overheating incidents in the past month." Hayes agreed to fly with an experimental cooling system that could potentially fail catastrophically at 25,000 feet over enemy territory. Franklin asked, "Yes, sir." His exact words were, "It can't be worse than what we've got now." The major nodded grimly. "Fair assessment. How long to install it on the aircraft?" 6 hours per engine. "I've already prepared the components for all 4. Do engines 3 and 4 first," Franklin ordered. "Those are the critical ones on most missions. We'll test it on tomorrow's milk run to France before risking it on a deep penetration mission." As the morning light filtered through the hangar windows, Donovan gathered his tools. The real test lay ahead, not just of his engineering solution, but of the Army Air Force's willingness to embrace unofficial innovation from a non-commissioned officer with no formal engineering training. "If this works," Major Franklin said quietly, "keep it quiet. If it fails—" "I know, sir," Donovan replied. "It was all my idea." July 16th, 1944. Aboard B-17G, Angel of Vengeance, 28,000 feet above occupied France. "The temperature readings," Captain Hayes called through the intercom. Technical Sergeant Donovan hunched over his clipboard, recording the precise readings from each engine. The B-17 had been airborne for 3 hours, participating in a bombing mission against railway marshalling yards near Metz and France. The real mission, however, was the unauthorized testing of Donovan's cooling system modifications. Number 1 engine, 221 degrees Celsius. Number 2, 218 degrees. Number 3 with modification, 207 degrees. Number 4 with modification, 204 degrees. The numbers told the story better than any technical report could. The modified engines were running a full 14 degrees cooler than their unmodified counterparts, despite identical power settings and atmospheric conditions. Captain Hayes's voice crackled over the intercom. "Confirm those readings, Sergeant. Number 3 is running cooler than 1 and 2. "Affirmative," Donovan replied, double-checking his instruments. "Both modified engines are maintaining lower temperatures throughout the power range. Oil pressure is higher and more stable as well." The data validated what Donovan had theorized. By redirecting cooling airflow specifically to the rear cylinder bank, the Achilles heel of the R-1820 engine, he had resolved the fundamental flaw that had plagued the B-17 fleet for years. The front cylinders still received adequate cooling, while the previously overheating rear bank now operated within safe parameters. "Beginning maximum power test," Hayes announced. "All engines to military power for 3 minutes." Donovan watched the gauges intently as the throttles pushed forward and the massive aircraft surged ahead. The real test would come now, sustained operation at the highest power settings, the conditions under which engine failures typically occurred. The temperature gauges for engines 1 and 2 immediately began climbing, quickly approaching their redline limits. But engines 3 and 4, equipped with Donovan's modification, stabilized at temperatures well within the safe operating range. "Results consistent through military power test," Donovan reported. modified engines maintaining temperatures approximately 17 degrees lower than unmodified engines at maximum power. For the next hour, the crew put the aircraft through increasingly demanding tests, pushing the engines to their limits while recording precise performance data. In every scenario, the modified engines outperformed their standard counterparts, maintaining safer operating temperatures with no measurable loss in power or fuel efficiency. As they turned for home, the bomber encountered a patrol of 4 Focke-Wulf 190 fighters. Captain Hayes put the Fortress into a diving turn, engines at full military power, as the German fighters pressed their attack. The 50 caliber machine guns chattered in defense while the aircraft maneuvered violently. Under normal circumstances, this type of emergency maneuver at high power settings would push the engines, particularly numbers 3 and 4 on the starboard side, into dangerous overheating conditions. But the modified engines handled the strain without complaint, their temperature gauges holding steady in the safe range. When they finally landed at Ridgewell, the ground crew immediately surrounded the aircraft. Major Franklin waited on the tarmac, his expression giving nothing away, as Donovan descended from the bomber with his clipboard of data. "Results?" Franklin asked simply. "Better than projected, sir," Donovan replied, handing over the meticulously recorded temperature logs. 17-degree average reduction in cylinder head temperature across all power settings. Oil pressure maintained within ideal parameters even during maximum power emergency maneuvers. Franklin studied the numbers, his eyebrows rising slightly. "No performance penalty. None we could measure. Captain Hayes reports normal handling characteristics and power response. If anything, the engines seem to be delivering more consistent power at altitude." "Because they're not on the verge of failing," Hayes interjected, approaching from the aircraft. "Major, we encountered FW-190s near the target. Had to go to military power while maneuvering. Those modified engines didn't even flinch. Normally, we'd be sweating a shutdown after that kind of stress." Major Franklin looked from the data to the aircraft, then back to Donovan. "How quickly can you modify the remaining engines on this aircraft? And how many others can we convert with the materials on hand?" 24 hours to complete this aircraft, sir. As for others, I've prepared enough components for 6 more B-17s using salvaged materials. With proper support, we could modify the entire group within 2 weeks. Franklin handed back the clipboard. "You have 48 hours to complete this aircraft and 1 more. If the second test is successful, I'll take this to Colonel Atkinson for group-wide implementation." As the Major walked away, Captain Hayes clapped Donovan on the shoulder. "How's it feel to have saved a few hundred lives today, Sergeant?" Donovan watched the ground crew already beginning work on the unmodified engines. "Ask me after Berlin," he said quietly. "That's the real test." February 3rd, 1945. Berlin raid. 29,000 feet above Germany. The formation of 23 B-17Gs from the 381st Bombardment Group cruised through the frigid sky, their contrails marking a precise line toward the heart of the Third Reich. Not a single aircraft had aborted the mission due to engine problems, an unprecedented achievement for such a long-range operation. In the lead aircraft, Technical Sergeant Donovan monitored his gauges with professional detachment, though he couldn't completely suppress a sense of pride. 7 months after his unauthorized modification had been tested, all 92 engines in the formation now incorporated his cooling system design. "To 5 minutes to rally point," Captain Hayes announced, "all engines performing nominal." The Berlin raid represented the ultimate test: maximum range, maximum altitude, and maximum exposure to enemy defenses. Yet the formation remained intact, each aircraft maintaining its precise position with engines running at optimal temperature despite the punishing conditions. In the months since Donovan's cooling modification had been implemented, the 301st had experienced an 83% reduction in engine-related mission aborts. More significantly, They had not lost a single aircraft to engine fires, previously their most common cause of combat losses after direct enemy action. "Bogies, 3 o'clock high," called the radio operator. Me-262s, looks like 4 of them. The German jet fighters represented the Luftwaffe's last technological advantage, aircraft capable of outrunning even the P-51 Mustang escorts that protected the bomber formations. As the sleek shapes dove toward the formation, the B-17 gunners tracked them with their 50 caliber machine guns, knowing the odds of hitting the fast-moving targets were slim. 2 of the jets focused their attack on the formation's lead aircraft. Captain Hayes threw the B-17 into a tight defensive turn, pushing all 4 engines to emergency power, a setting that would typically guarantee overheating and potential failure within minutes. Donovan watched his temperature gauges like a hawk as the aerial battle unfolded around them. The modified cooling system performed flawlessly, keeping cylinder head temperatures within safe limits despite the extreme demand for power. The Me-262s made a single pass before breaking away, unwilling to linger in the defensive crossfire of multiple B-17s. As the formation straightened out, Donovan noted with satisfaction that not a single aircraft had fallen out of position due to engine problems, something that would have been unthinkable during similar missions just months earlier. When they finally landed back at Ridgewell after 9 grueling hours in the air, the entire formation had returned. 3 aircraft showed battle damage from flak and fighter attacks, but all had completed the mission successfully. For the maintenance crews who had worked tirelessly to implement Donovan's modification across the group, it was vindication of their efforts. Colonel Atkinson, the group commander, met Donovan on the tarmac. "The numbers came in from 8th Air Force HQ," he said without preamble. "Yeah. Since implementing your cooling system modification, the 381st has the lowest engine-related abort rate in the entire 8th. General Doolittle wants to know how we did it." "Just a simple airflow redistribution, sir," Donovan replied modestly. "Simple or not, it's being implemented across all B-17 groups in the European theater. Boeing engineers are here to document the modification for inclusion in the official technical orders." The validation of his work by the manufacturer was something Donovan hadn't expected. What had begun as a desperate field modification, born of necessity and implemented despite regulations, had become standardized doctrine. In the months that followed, Donovan's cooling system modification was installed on hundreds of B-17s throughout the 8th Air Force, saving untold numbers of aircraft and crews from the fate that had claimed so many before. The design was eventually incorporated into the technical manuals, though the official documentation never credited the sergeant who had first conceived it. By April 1945, as the air war over Germany reached its climax, the B-17 fleet operated with a reliability that would have seemed impossible a year earlier. Engine-related losses dropped to negligible levels, allowing the massive formations to maintain their combat integrity through the most demanding missions. Technical Sergeant James Donovan received the Bronze Star for his contribution, the citation carefully worded to avoid revealing the unauthorized nature of his initial work. But among the crews of the 381st Bombardment Group, the modification became known simply as Donovan's Fix, the improvisation that had transformed their vulnerable aircraft into the true flying fortresses they were meant to be. Official USAF Technical Analysis Report, dated May 1945, recorded, "Cylinder head temperature reduction modifications implemented across B-17G fleet resulted in 78% decrease in engine-related combat losses during deep penetration missions. Estimated 123 aircraft and 1,230 airmen saved through this engineering improvement alone during the final 6 months of the European air campaign."